quite that good. Okay, this is a presentation. I get to pretend to be Rob Pettit from the Aerospace Corporation. He was to deliver this presentation at last year's Flight Software Workshop, and those of you that were here may remember that the East Coast was snowed in, and he couldn't, there were no planes leaving, and so he was stuck. And amazingly enough, this year, he has work to do, and so his supervisor said, "You're not going anywhere." So he asked if I would do these. So this is, what I want to talk about is why model-based activities are needed, but there's not enough knowledge yet. We need more knowledge to make it really good. Okay, so this is, why do we want to do this? I love this quote. As the complexity of current systems has grown, the effort needed to certify them has risen to account for more than half the total system cost. That is spooky. National Science Foundation in 2009. I know you guys don't think so, but software is a contributor to mission anomalies, and not yours. I know. It's good to look at things long before you get to code. And I think we've heard that several times yesterday and today. Requirements, the architecture, the design, the performance, reliability and safety, fault management. God, that's like the worst thing to do, right, is put fault management after you've got the system well underway. Good luck. It's not clear what you're going to save yourself from. The problem that goes with it is you can't test everything, and so you need to be able to verify the design and the implementation in other ways, probably formal methods. Model-based techniques show promise for this in addressing complexity and some of these early challenges. And there have been successes. I think NASA LADI was a just ginormous success. Anyway, but there are many things that we have to learn for large-scale adoption. Here's a chart. You can just sort of see how software grows in software lines of code. From 1965, next to nothing, 2005, I don't know, that's way up high on the other end. It grows in complexity as well. Half of all modern space systems anomalies are due to software. That's pretty spooky, and I couldn't say it if it weren't published. Actually, Myron Hecht and Doug Bittner, who you may remember from previous flight software workshops, published that in Software Testing and Space Programs in a Crosslink magazine a little while ago. I'll give you another example for growing in complexity and size, but it's not on the chart, but it's shown up in years gone by. How many of you remember the first Apollo mission? None of you, you're too young. How many lines of code? Do you remember? It's 10,000. How many lines of code when they go back? Do you know the answer? It's 10 million. Yeah. That's a NASA number. I couldn't make that up. Software-related failures, take a look. They just grow gigantically. All over the world, it's everybody's systems, because they're so complex. What is it that's special about spaceflight software? No direct user interface. It's an embedded system with lots of hardware devices. Requires scientific and engineering knowledge that's way more complicated than normal applications. You have a rad-hard processor that is God knows how many generations behind. And you have loads of real-time requirements, which is really tricky to do. This last bullet down here, it looks innocuous, right? If I had a mouse, you could see it. Small compounding errors create major problems. Let me take a brief aside here and recommend, those of you with copious spare time, let me recommend a book to you, Normal Accidents. If you haven't read it, you know, it's worth spending a week in the evenings and reading that. It's the story of the 3 Mile Island disaster by a contractor who was hired by the government to investigate it. But he investigates spacecraft accidents, 3 Mile Islands, a whole bunch of things, and they're often the result of something small going wrong. The operator thinks it's okay. Something else goes wrong. It presents a situation the operator has never seen before, and now they don't know what to do. It happens in spacecraft as well. Okay. Oh, that would... And that concludes my talk. Sorry. This will all look familiar. Modeling and analysis for risk mitigation. So early modeling and analysis can reduce incidental complexity. It can also actually help to guarantee that your architecture is suitable for the implementation. I will tell you that I used to be, in years gone by, because I'm old, a program manager, and I paid people a lot of money to develop a model of my system that executed, not in real time, but I could watch the system execute and see what kind of additional resources were needed if I made changes. So as people checked in code, we got the code running, we also instrumented how long their processing was taking, and then we updated the model. And our customer bought into this, so that when they would come back to us and say, hey, we need you to make a change, how much is it going to cost? We would actually put it in the model and say, the cost isn't the issue, you're going to have a performance problem here and here unless you pony up for more hardware or whatever. It's critical to have that, I'm just saying. Okay. Modeling will help you with the trade studies. It'll point to problems in performance like I'm describing, and help locate potential issues such as deadlock and race conditions. There are a lot of ways to locate deadlock and race conditions. JPL is locked into Spin and Promella, I think, for a super good reason, right, because they had a failure quite a while ago. It's important to do that stuff. Some of the challenges with model-based activities. There have been a lot of successes with small things that are often very deterministic. So individual little subsystems that are very deterministic work well. Lots of clear control laws. It works well. There are challenges for scaling up. Integrating multiple languages, lack of coordinated development approach. You guys, everybody should actually be using as much of the same approach as possible. If you have model-based code, model-based auto-generated code, how are you going to link that into everybody else's code? Verification and validation of the code is really tricky. Some of the tools give you a nice technique where you can draw out pictures of your design, yeah? And then you can create test suites that you can test your design on, and hopefully if you're good, you'll do robust testing of your design. And when you auto-generate the code, you can test it. You know what? Almost nobody's code comes through clean. There are still today bugs in auto-generated code. It's important, you got to, he doesn't have these on the charts, but I'll tell you. It's important to have run rules to know what to do with those. Okay? Has anybody looked at auto-generated code? How pretty is it? Yeah, right. It's super ugly. Sometimes super ugly. Oh, maybe not yours, other people's. It was somebody else's child. Sometimes they're really hard and ugly to wend your way through. It's not the prettiest code to look through. And you have to ask yourself, do I want to make changes to the auto-generated code, or do I want to do something a little bit different in the design to try and fix it? Run rules like that are incredibly important to have up front, because I got to tell you, when you come to the crunch, when you're doing that 15-month satellite mission, like we heard this morning, you know, when it gets to be crunch time, you have to know exactly what the rule is to do, because making it up is failure. I mean, it's just too hard to do. Model-based engineering versus engineering with models. Well, we kind of talked about that a little bit. There are lots of advice. There are lots of tutorials. There are lots of guidelines. ISORC, for those of you who are interested in spending 3 days doing that, the IEEE has a conference on that. Pardon me? In New Zealand. Gabor is one of, yeah, he's one of the organizers. And Rob Pettit is one of the organizers. And I think I heard from somebody that there's a European Standards Commission on, where are you? On aviation spacecraft, aviation flight software, model-based, right? It's not mature yet. They need people to set up standards to help to make that work. There's little or no model-based engineering development methodology for large-scale systems. I know we've seen Lockheed. Where's Mike? Ah, there he is. He actually funded one of his people 3 years ago, 2 years ago, I can't remember, to do a double-blind study to see what is the benefit. And I think they found about a 1/3 benefit, plus or minus, doing model-based over hand-coded, coming out with essentially the same code when they were done. But this is new and in its infancy. And I got to tell you, one of the other items as part of, since I work at aerospace, one of the things that we have to deal with is the acquisition end of these things. If you come to us and you say, I'm generating software, and here's what I know. I know function points, I know lines of code, it looks like this other code I have. We can come up with a schedule and a resource estimate for you. You know what? If you come up with a model, it's not so easy. So this is a new part of the world. How do you develop what it really takes to build the model and to accurately test the model? These are subtle things, and work is needed. Okay. And there's an absence of defined methodology. So integration of multiple modeling languages, it is done, but different disciplines typically use different modeling languages. In spaceflight software, spacecraft engineers are responsible for the flight control software, often use MATLAB and Simulink. Application software engineers are responsible for onboard things like fault management and whatnot, often use UML. I don't see Roche here, but Roche at JPL was using Magic Draw for one of the Mars projects and actually generated his own code generator for using Magic Draw. So, variety of different tools. Integrating the languages across the system is difficult. It takes a lot of communication amongst the stakeholders to see that that works. CM, also a trouble area, and interfacing the system components across the languages and across the models is hard. Don't hit the end button. Verification and validation. Model-based engineering approaches to facilitate V&V of the design compared to the informal models. It is really important to get the independent verification of the software and the robust enough way to do it. You heard how Laddie did it. They didn't write a line of code until they knew exactly how they were going to test it. Everything. Good practice. Executable models enhance verification and validation. The more models you can give people to work with as they develop, the better it's going to be at the end. Verification of requirements, tracing. Now this is, Rob didn't put this in, but this is actually an area of active research, tracing the requirements into the model, into the code. There's a fellow up at NASA Ames. I'm so embarrassed I don't remember his name. It's Sean something. Yes. Say it again, please. Johann Schumann. He's actually, it's an active area of investigation. What kind of tags do I have to put into my model so that when I go and inspect the code, because he doesn't trust anybody's auto-generator, when I go in to look at the code, I can see where the critical requirements are executed and that the code that was auto-generated is suitable for the application. So there's a lot of subtlety there. But it's still an active area of academic research. Okay. Code and model consistency. Inconsistencies between models and implementation are a serious problem. So what do? You have to have these run rules up front to decide if I'm going to use model-based development. When I have to change code, what am I going to do? When there's an update to my flight software that's in a model, what do? Am I going to go fix code, or am I going to go fix a model and re-auto-generate the code? I'm not telling you there's a right way and a wrong way. I'm saying write down what you're going to do and be sure that everybody knows. Okay. Capturing and verifying the critical parameters. Many of the quality of service aspects need to be captured in the flight software. The real-time properties, the reliability, the failure modes, fault detection. It requires the use of domain-specific language extensions. You can use MART for UML. Simulink's aerospace block set is usable, but they're not used consistently and effectively across programs. Programs often use their own specialized profiles. Not a bad thing, but just make sure that anybody else who's looking at it is aware of it. Model-based engineering has versus engineering with models. Model-based engineering has models that are the primary artifact with consistent artifacts and fully specified models. Engineering with models, the models are used to illustrate the design. They have inconsistent artifacts, lightly specified models, right? There are some accuracy issues, and commonly applied in model-based activities or efforts. So, what's the conclusion? Size and complexity of the spaceflight software is only going to get more complex. We're going to do more and more with software. Model-based software engineering has promise. We've seen it can reduce cost and be effective, but you have to address the complexity. You have to have early analysis to make sure you're going down the right path and that the model you're generating is supportable and testable. And did I say robustly testable? I really meant that. Not nominally testable. You got to know how you're going to fail. That means, did I say this? ConOps for failure. I'm on the podium, I can say it. You need a ConOps for failure. Just write down how you want the system to fail and then put it in the model. Okay. It can reduce the disconnect between design and the implementation. There's nothing worse than getting towards the end of the program and finding out that all the documents you wrote down are useless. Don't do that, right? When changes go in, make sure the design in the model is updated every time. That's everybody's artifact. But now there is a gap that remains for scaling the model methods to large, excuse me, mission-critical systems, and there's a gap on how to bid these into programs and how to make sure that they're suitable and accurate. Remember, there are people out there like aerospace, like me, that are going to have to go and, not all of you, but some of you have to go and look at your model and see, how do I know that this thing is exactly right? How will I test it and make sure? How will I make sure that it has all the off-nominal situations in it? And then how do we make sure that the code and the tests are accurate? Still big research and gap areas. Okay, so that's what I have. Questions?
So, Alan,
I'll repeat your question. Oh, can you take that? Go ahead. It's Andre up here. A little more. Yes, Andre. Yeah,
I know the complexity will increase and the lines of code will get worse, but is there like a threshold that makes sense to use model-based design versus just do it traditionally, without model-based?
No, there's not a threshold. There's not a threshold based on size.
Or the complexity?
Yes, there is a threshold based on complexity. What I was saying before is that right now, things that are very deterministic, that are easy to test through, are better candidates for high reliability systems in a model-based environment. So, for instance, if you're doing lots of, maybe complicated, but lots of basic mathematic things, like you're doing lots of linear algebra, that's a good candidate. You're not going to make mistakes with it, and it's easy to make sure that the design is right and the code is right. Things that are very complicated and perhaps have fuzzy results, like they may lend themselves to unusual fault condition, or you have to manage complicated fault conditions, would be very difficult to do and get correct.
So I want to just throw out this
Sure.
question to the community. I mean, we have a model-based architecture, model-based testing, model-based fault design you had. But really the benefit is really, if your goal is to really optimize the design or optimizing the test suite or optimize the fault management system, should that be the goal of the model-based engineering methodology, whatever you want to call it?
Let me give you one answer. One of the goals where the industry would go with this is that you don't necessarily have software experts developing the software system anymore. What you have are system engineers and hardware experts that are able to put the system together with a design like this, with a set of tools like this. That's good and bad. On the good side, you're getting the people that are most intimately familiar with the way the system should operate, drawing out how they want it to operate, and getting code that will do it. That's really good, because that's as close as you can get to the stakeholder of the item. The bad news is that there's still a lot of complexity in software that it's difficult to get all the system engineers and all the thermal people to learn right away. If you have a product line and you've actually tested your way through one core portion of it and it's model generated, and you know it's been V&V'd and you have minor changes to move it to the next product, build your company that way. Build up little pieces of it that way until you have a model system that you can, where you understand the areas of variation in order to make a new product. Do you understand what I'm saying?
Yeah. So I mean, before you start coding, you want to build you want to build a design or you want to build a model, right? And you find if you want to improve your design, then you work with the models, right? I mean, so in my mind, I mean that's why I want to use the model-based anything.
There's one step beyond, is that you have this good model, and then it clicks through and generates the software on which you have the automated test.
Right,
that
that's
verifies.
another issue, right? I mean, to me, I've used the rational rows, and then you go from the requirements to the design, and it will create some auto-generated code and whatnot. But what I'm saying is you want to use model-based anything because you have a room that you have a desire to improve your model, whether it's a base design or testing or whatever. I mean, that's why you build a model first, and then you start.
Absolutely, absolutely. I'm a firm believer. I just don't have enough knowledge in my hand yet. There's still gaps for me. So, other questions?
Yes.
Dr. Landauer.
It's curious. I just noticed you're talking about model-based design, acquisition, construction. But remember, the satellite is not the end goal of this. It's what the satellite's supposed to be doing. So how many people are doing model-based operations?
I don't have an answer. I don't see a lot of hands going up. Okay, good point. So model-based operations, good thing. So, did Laddie do that?
We had an activity planner that we basically modeled all of the activities in the spacecraft and then auto-coded out the sequences to run the spacecraft. So yeah, in effect, we did that.
Okay, so Laddie was a pathfinder for that. Very good. We shall go to work for you. Okay, that being said,
Kalani has a question.
okay. Oh, no.
This last question.
Oh, sorry.
Go ahead.
So you talked about model-based design and code development. In the morning, the first talk, we heard that 75% of the code was reused.
Yes.
So many of our systems use the existing software. How does model-based system relate to that environment? And most of the program that we have, if you take JPL Mars program or anything else, you use a lot of existing code.
All I'm going to tell you is it's hard to link in existing code with something that's model-based. It's really difficult. I'm not the guy. No, it is really hard to do that. However, one of the things you did hear earlier, I'll just say it real fast, is I think we heard it from ESA. Standards, standards, standards. Standards and APIs. Standards and APIs. If everybody builds to standards with known APIs, and I think Dr. Weiss said it as well, standards and APIs. If you do that, you can link them in. It doesn't matter how you came by it. You can link it in, and they can make it work. If you don't have it, if this is stuff that was developed, 20 years ago, good luck. Okay.
Using the existing code, and you're going to have to build a model for the new stuff.
Yep.
And that's what we are challenged with.
There is a traceability challenge. There is a challenge of care, and I'll talk about it another. But there is a challenge to be super careful to make sure things don't get missed and lost.
Okay, I guess.
Okay, I'm off.